Okay, dig in. This is probably going to be a pretty long video, and that's on top of the other ones. So this is your introduction to nuclear magnetic resonance. Probably a lot of you have experienced this through an MRI. Right? Cover up nuclear magnetic resonance imager is something humans crawl into and look at. Doctors look at the protons in your body. The reason an MRI is called an MRI, not a nuclear magnetic resonance imager, is because people don't like the word nuclear. Nobody wants to crawl inside something that's got nuclear on it, so we just drop that out. The way we're going to do NMR, and again, NMR is in organic chemistry the most powerful tool we have. Mass spec, due to computational advances, is coming up fast, but right now, a small molecule organic chemist likes NMR the most. So, we're going to take a sample, we're going to take our molecule, we're going to expose it to a really strong magnetic field. That's going to line all the magnetically active nuclei up with that field. Then we'll pump it with radio waves that will excite those nuclei, then we'll listen to them to relax. And so we're going to detect magnetically active nuclei. That's going to be protons. And so these are the only two we'll consider in this class. Protons, H's. 99.85% of hydrogen on Earth are simple protons, no neutrons in the nucleus. C13, on Earth, about 1% of the carbon is C13, right? So most carbon is C12. It's got 6 protons, 6 neutrons. C13 is an isotope of carbon that has 6 protons. Remember, an element's defined by the number of protons. So 6 protons and 7 neutrons. That odd number of nuclear particle gives the carbon, C13, gives the C13 a magnetic moment. All right, so we can line these up with an external magnetic field. There are a whole bunch of other magnetic nuclei, and in theory, you can do NMR on any magnetically active nucleus. So O17, N15, I think phosphorus, something, sulfur 33. Anyway, you get the idea. In this class, we're just going to look at protons and carbons. We'll look at protons next time. Proton NMR gives us a lot more information than C13. It's sort of it would be an overload right now. You're probably sitting there at home saying, dude, it's already an overload. Like, you can't make it worse. I can make it worse. Proton NMR has a ton more information. I want you to get C13 NMR down first, and then we'll go talk about proton NMR. So again, the information we're going to get out of an NMR spectrum is the local magnetic environment of those nuclei, right? If we got one peak, if every proton in the universe gave us a single peak in the NMR, we wouldn't learn anything. It'd be like, oh, you got protons. Well, we knew that. You got carbons. Well, we knew that. So depending on the atoms around it, remember, atoms and bonds are electrons. You've got all this electronic stuff going around this little magnet that affects the magnetic environment of the nucleus, right? If I'm a proton and I've got like a chlorine here, I'm in a different electronic environment than if I'm a proton and I've got a nitrogen here, right? So we'll see different little signals. And ultimately, using a proton NMR and C13 NMR and some more sophisticated stuff, you can piece together, and you can take just spectra. You can start with no idea what the molecule is. You can take an NMR and you can figure out what the molecule is. You're not going to have to go quite that far in this class. 4 minutes on slide 1. Drink. All right. So here's what we're doing. We've got all these magnetically active nuclei, and in the absence of a magnetic field, they're just kind of tumbling around randomly. Apply a really strong field, and all of them will line up. You guys have seen this with magnets, right? Magnets will line themselves up with each other. So this is our ground state. No, sorry, that's not it. We can't do spectroscopy here. This is going to be our ground state. All the magnetically active nuclei lined up with the external magnetic field. So, spin aligned is our ground state. Spin against is our excited state. I talked about these in the intro to spectroscopy. To do spectroscopy, you always need a ground and an excited state. All right? So if I take a magnet and I line up, like if I expose a magnet to a magnetic field, the magnet's going to want to line up with that field. The next easiest way for that magnet to behave is to line up exactly opposite. So if I pump energy in, if I pump the right photon in, I can go from the ground state to the excited state. And again, the photon absorbed has to exactly equal, right? The photon that gets absorbed there has to exactly equal the energy difference between those two states. It turns out that energy difference is equal to a radio photon, right? A radio wave. The other interesting thing about NMR is that energy gap, this energy gap is proportional to the magnetic field. If I apply a stronger field, that gap grows. Weaker field, that gap shrinks. And so we typically classify our NMR spectrometers by the gap in energy, by that energy gap for a proton. So the NMR in Salem Hall is a 400 megahertz NMR. It means when you put a proton into the NMR, ground and excited state are going to be separated by about 400 gigahertz. All right, there's a lot of physics there. It's really cool. Again, Chem 334, Chem 342. There's some grad courses in it. We'll actually, all of you will go see the NMR. We're going to do an experiment later in the semester where we use NMR to measure a reaction rate. And you'll see the NMR. You won't have to actually take the NMR. So there's a ton of physics here. And it's really cool physics if you like that sort of thing. But you guys just need to take home the bullet points right now. All right. So what do we get from a C13 NMR? Well, we get chemical shift. This is frequency. All right. And what that's going to tell us is what type of environment the carbon is in. All right. So is it in a double bond? Is it in a double bond with oxygen? Is it next to an OH? Is it bonded to a carbon? Is it bonded to an OH? And then the other thing we get is information about molecular symmetry. We get the number of magnetically unique carbons. Okay, so a molecule may have 10 carbons, but 4 of them are the same, and so we only get 6 signals. All right, we'll see that more in a minute too. All right, so again, I just jump right in. I'm checking to make sure none of these lines fall in the cracks, and they don't. So up at the top, you see a molecule, right? Here's our molecule, and here's the C13 NMR. So here's what a C13 NMR looks like. Basically, the y-axis doesn't tell us anything. In a C13, the y-axis is essentially meaningless. This is a synthesized spectrum, so it's not quite meaningless. And then the frequency axis is always going to be in parts per million. And that is, we have a reference, so at 0 is a molecule called tetramethylsilane. Right, so silicon bonded to 4 methyls. The peak corresponding to the carbon in tetramethylsilane, we set at 0. And so we're looking at the energy shift from TMS. Again, I'm not going to ask you mathematical questions about this. And the other thing to look at is in this molecule, this goes back to molecular symmetry, all 4 of these carbons are magnetically equivalent. They're chemically equivalent. All right, we can't tell them apart. There's one signal there. All right, so you're always going to see 0 to like 180, 200, something like that. Typically, this is going to be 0 to 200 or 250 or something like that. It might be less, like we may zoom in. If there's nothing left of 60, I'm going to zoom in to 0 and 60. And then you're just going to see a peak, right? This corresponds to a carbon. Each peak corresponds to carbon. Right, so in an NMR spectrum, the nucleus you're looking at is important. So in a C13 NMR, every peak here corresponds to a C13, and only a C13. You're not going to have a peak for an H. You're not going to have a peak for a chlorine. You're only going to have peaks for carbon. Right? So you're going to have to infer from where on the frequency axis, the chemical shift axis, that peak happens as to what it's bonded to. So you remember in IR, we had a spectrum, and it was like XH, triple bonds, double bonds, fingerprint region. We're going to do the same thing for the C13. Next thing. So here we go. I'm going to erase some stuff. I'll leave TMS down there. Okay. So here's this molecule is called TMS. You might see it in the book that way. Right. So as you look, the less electron density there is around a carbon, the farther downfield it will come. So a couple of terms here. Downfield in NMR is to the left. De-shielded. So downfield, upfield is just like port and starboard. Words for left and right that I don't know why they're there. Downfield is to the left in an NMR, upfield then is to the right. De-shielded means there's less electrons around the carbon. And so you see carbon-oxygen double bonds way down on the left, right? And remember, there's this resonance structure. Right? That oxygen's pulling electrons away from that carbon really strongly. Okay, so carbonyls of all sorts are going to kind of come to the left. You want to use this in conjunction with the IR, which we just did. Right? In the IR, there's this big peak right in the center of the infrared spectrum. If you see that peak, you've got to have at least one carbonyl peak in the C13 NMR, and vice versa. If I see a peak down here on the left, I've got to have a carbonyl in the IR, right? And then again, down sort of 110 to 160-ish, carbon-carbon double bonds. And again, the peak strength is not that useful right now. You just want to note that you've got peaks. So carbon-carbon double bonds, just a little bit upfield to the right of a carbonyl. This molecule doesn't have any sp carbons, but if you did, it would be somewhere here in the middle. Down on the right are going to be sp3 carbons, right? So upfield, we're shielded, right? More electron density around the C. So upfield is to the right. We say that's shielded. Those carbons are going to have more electron density around them. So on the sp3 carbons, so this is sp3. I should say this here. Sorry. sp3 carbons bonded to an electronegative atom. This could be O, Cl, N, etc. Right. So an sp3 carbon bonded to an electronegative atom is going to be kind of 50 to 90. And then all the way on the right are just going to be sp3 carbons, right? sp3 carbons bonded to other sp3 carbons, maybe an sp2 carbon. Nothing especially electronegative near it. So it's got more electron density around it. So again, right now, everything in this class is open note, open book. You can use this PowerPoint. So you don't have to memorize this. My goal would be that you would memorize this by working the problems. That's how I memorized it. That's the best way to memorize something, is to work with it. Oh, the other thing I wanted to say before I go on to the next slide, in these regions, so like in this 50 to 90 region, you'll see a carbon that's not bonded to hydrogen left of a carbon bonded to one hydrogen. Carbon bonded to one hydrogen will be the left of a CH2. CH2 is going to be the left of a CH3. Just wave my colleagues. Okay, that's a lot to take in. You can pause, sit down, take some notes, go for a walk, throw darts at my picture, whatever you want to do. But you're going to need to get all that information in at some point. Okay, so now I want you to hit pause. count up the molecular formula of this molecule. Right? This comes out of the line structure stuff we've been doing. And then count how many peaks you have in your C13 NMR. So hit pause and do that. I take a drink of tea every time I tell you to hit pause. All right, so you're back. Let's see what our molecular formula is. Our molecular formula is C16H24O2. The O2 is easy. 16, you got to count them up. Hydrogens get hard to count, but this is going to be unsaturated, right? So 16, 2 times 16 is 32, plus 2 is 34. So 34 minus 24. Right, 34 minus 24, 10, divided by 2, this is going to be 5 units of unsaturation. 5 units of unsaturation, rings are pi bonds. That's off. 2n plus 2 minus 2n is 32. Oh, right, never mind, it's there. Sorry, I miscounted. Doing arithmetic. Here I'm telling you to do, you really should take Pchem 2. It's a great class. It's not arithmetic. It's like differential equations and stuff, so you don't have to do arithmetic, which is painful. 5 units of unsaturation, 4 pi bonds. Count the pi bonds. 1, 2, 3, 4. And then 1 ring. So 4 pi bonds in a ring is 5 units of unsaturation. Okay, so that all fits. So how many signals did you get in the carbon NMR? If you haven't, hit pause and count those. There's only 12 signals. Let's put a number by them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 signals in the C13, but there's 16 carbons in the molecule. That's no good. Actually, it's fine, all right? The number of signals is going to give us information on molecular symmetry. So right here, right, we get information on chemical shift based on these color-coded things. So let's go through that. I probably should have done that first. Carbon 1 is going to be a carbonyl. We can assign that right now. Right? We've got 1 carbonyl carbon. We've got 1 carbonyl carbon down, all the way downfield. Carbon-carbon double bonds, 110 to 160. There are 4. 1, 2, 3, 4, 5, 6. So this is going to be, what is that going to be? 2 through 5. 2 through 5, peaks 2 through 5 are going to correspond to that ring. But right now, we're not sure how. All right, and then carbon 6 is easy. A carbon bonded to an electronegative atom. Carbon 6, about 65 parts per million. There's 1 carbon bonded to an oxygen. So that's carbon 6. 7 through 12 are the rest. 1, 2, 3, 4, 5, 6. That's 7 through 12. We also have these 2 down here. Right? So sp3 carbons, not bonded to anything electronegative, all the way upfield on the right. And we've got too many of those as well. So we have to figure that out. So the fact that we have fewer signals than we do carbons in the molecule gives us information about molecular symmetry. I'm going to go away from this molecule for a moment to a different molecule. I'm going to erase my stuff here too. You can always go back and look at that. You've got a rewind button, unlike class. All right, so take this slightly simpler molecule. How many different carbons are there? Well, just how many carbons are there first? Hit pause, count the carbons. All right, you're back there, 8. 6 in the ring, 7, 8. All right, let's put up, well, I guess I don't have a spectrum for it, do I? Shoot, that would have been nice. Let me just ask you, how many, hit pause and think about how many different carbons there are. Whatever that means to you. Okay, now that you're back, there's 2 ways to sort of analytically decide if two atoms in a molecule are equivalent or not. The first and best way is to look at a line of symmetry. All right? This molecule's got a line of symmetry down the middle. It's also got a line of symmetry that's not important for this exercise through the plane of the board. Right? All of these are sp2 carbons. They're trigonoplanar, so they're flat. And so there's a line of symmetry through the plane of the board. This molecule is a flat molecule. Let's go on. All right. But the line of symmetry here, and it may not, you might say, well, wait a minute, the H is right in the line of symmetry. Single bonds, this is an important, there is what we call free rotation around single bonds. Right? So if I've got something that looks like this, right now, these four are all in the plane. That's a single bond, so it can rotate. This can go back and forth like that, right? So this H can be on the same side as this H, or it can be opposite. And that can just go round and round. And single bonds, in fact, in molecules spin wildly, hundreds of billions of times a second. They really spin crazy. So this OH is drawn to the right, but that's a single bond. And so really that OH is defining a cone here. The same thing for these methyls, they spin, so you get the plane of symmetry through the board. Okay, so now, given that plane of symmetry, does that tell you anything? Can you pause if you want? All right. So atoms reflected by a plane of symmetry or a line of symmetry are magnetically equivalent. They're going to give one signal. So for instance, these two, those are the same, right? They're reflected in the plane of symmetry. If you think about that, the NMR spectrum is giving us information about the magnetic environment around an atom. This carbon is in a benzene ring. It's bonded to an sp2 carbon with a methyl and an sp2 carbon with an OH. It's directly across the ring from an sp2 carbon with a methyl, and it's 1 over from sp2 carbons with H's. All of that fits exactly with this one, right? sp2 carbon bonded to an sp2 carbon with a methyl, an sp2 carbon with an OH, across from an sp2 carbon with a methyl, and one off sp2 carbons with an H. The electronic environment around those two circled carbons is exactly the same. So they're going to give one signal. There's two atoms there, but they're going to have the same energy gap in the magnetic field, right? And then the same is true of these two carbons, and finally these two carbons, right? So in the C13 NMR, you would expect to see 1, 2, 3, 4, 5 signals. There are 8 carbons, but there's only going to be 5 signals in the C13 NMR. Remember, the oxygen, none of the hydrogens show up. You can only infer information about the oxygen and hydrogen, the non-carbon atoms, in a C13 NMR. The other way to do this is not to use the line of symmetry, but to do what's called a replacement test. So, let's look at the two black circled carbons, Ca and C. Let's call them Ca and Cb. And then what you do is you replace Ca with X, then you replace Cb with X, and you ask yourself if they're the same molecule or not. So here we've replaced Ca with X, here we've replaced Cb with X. Now are those the same structure? And again, this may be, you guys are just learning to use structure, so this can be a little tricky, but those are the same molecule. Imagine I take the one on the right where I've replaced Cb and I pick it up, and I turn it over, and I lay it here. It overlays precisely, right? And so those are the same molecule. Those compounds are the same. And because they're the same, that means, so these compounds are the same, and that means Ca and Cb are equivalent, right? If you do a chemical reaction with this molecule, Ca and Cb will react the same. If you take an NMR spectrum of the molecule, Ca and Cb will give one signal, the same signal. And in fact, the protons on Ca and Cb and the proton NMR will give the same signal. So being able to determine magnetic equivalence, chemical equivalence is really important. I'm going to put a note in here. Yes, more. All right, this all gets a little more complicated in chapter 5, stereochemistry. All right, you've got a couple of more things to consider there. But for right now, I'm gonna leave stereochemistry out of this, I promise. All right, so let's go back to our original molecule. No, just again, oh crap. Let's go back to our original molecule. I have to go back, sorry. All right, here's our original molecule. Let's look at our planes of symmetry, like what's the same. So we get a plane of symmetry here, line of symmetry there. And again, this single bond rotates freely. So this whole thing is sometimes up there, sometimes down here. But basically, these are the same, and the methyls are the same. It's exactly the same as the last one. So remember, this was supposed to be 2 through 5. I should number these again, sorry. So 1 is the carbonyl, and then I'm not assigning these, but I'm just going to go with the number 2, 3, 4, 5. All right, that one is 3 then, reflected in the plane of symmetry. This one is 4. Right, so that benzene ring only has 4 signals due to the symmetry. 6 is by itself. And then we need 7 through 12. So let's just do this. 7, 8, 9, 10. You can't find a difference there. And again, these aren't, I'm just counting right now. I'm not assigning signals. Right? 7, 8, 9, and 10. There's no plane of symmetry that gives you another molecule, right? This is a CH2 bonded to a CH2O. That's a CH2 bonded to a CH2, CH2, but no O's as close. So 7, 8, 9, and 10 are all different. The CH is obviously different than any CH2. So we've got 2 signals left, 11 and 12, and we've got 4 methyl groups. But if you look, these 2 are reflected in the plane of symmetry, so those could both be 11. And then these 2 methyls, again, plane of symmetry there, they're both bonded to the same methyl. They're all freely rotating, and so these are 12. And so we've got the right carbons in there. Okay? So now let's rush forward again. And this is kind of like the IR. If you want to hit, this would be a good place to hit pause and just go like decompress for a minute, or you can just keep going right into it. You guys are young, making you feel good. I know I need lunch. All right, so just like in that last exercise with the infrared spectrum, this becomes a process of elimination. You can't really use C13 NMR to piece together an entire molecule either. You can get a lot more information than an IR, but not quite enough to do the whole thing. Again, I've put our sort of what corresponds, what type of carbons fall where on the chemical shift axis, giving you 6 candidate molecules. And I've given you a C13 NMR spectrum, and I'm asking you to tell me which molecule fits. Molecule or molecules, doesn't have to just be one. So hit pause and give it a try. My drink, we need pause. Alrighty, so how many signals, first of all? 1, 2, 3, 4, 5, 6, 7. There are 7 different signals. Right, we're not going to get information about OHs, so we can't just look at OH, OCH3, differences, carboxylic acid. None of that falls. We're only looking at carbons. All these molecules have carbons. But there's 7 different signals, and there's some symmetry in some of them. Draw the lines of symmetry. Right, so If we look at this molecule on the left, 1, 2, 3, 4, 5 different types of carbons, right? These two are reflected, these two are reflected. 1, 2, 3, 4, 5, again, reflected, reflected. 5 signals here. Those are out. 1, 2, 3, 4, 5, 6. 6 is not 5. And the other thing you might notice, that's an sp3 carbon. Are there any sp3 carbons in this molecule? No. There's no sp3 out here. Okay? So we can rule this one out. Same thing here. 1, 2, 3, 4, 5, 6, and an sp3. So that one's out. How about the one on the far right? So 1, 2, well, okay, there's no plane of symmetry. 1, 2, 3, 4, 5, 6, 7. 7 carbons, good. But these are all sp3, right? 6-membered rings aren't benzenes necessarily. You have to have double bonds. These are all sp3 hybridized. There's none. There's an sp2 up there, but there's just one. These are sp2, right? Aromatic alkene, sp2CHs, or carbons. So this one's out. There you go. That leaves one. Process of elimination is great, but don't just rely on that last one. So here you go. How many carbon signals should we see there? No plane of symmetry. Well, there's a plane of symmetry through the board, but not overall. So there's 1, 2, 3, 4, 5, 6, 7. There are 7 carbons. Got a carbonyl carbon, 167. That's carbon 1. The benzene carbons, there's no way at this point for you guys to differentiate which one is which, but you've got, they're all different. All 6 of those benzene carbons are different. 1, 2, 3, 4. That's why this is here. One of these is doubled up. That one is doubled up. 120, 0.02, 119 on screen can't be differentiated. So this is our carbonyl. 1, 2, 3, 4, 5, 6. The 6 benzenes are all different. So this is our molecule. Yay, you got one. All right, let's do one more. Now that you've seen that, I've got one more for you. Same set of molecules. Same set of molecules. Figure out which one applies. 32 minutes, Lord. Hit pause, figure it out. Okie doke. So, here we've only got 5 signals. We still have no sp3 carbons, right? There's nothing to the right of 80, there's no sp3 in this molecule. And so we can rule this one out. And we can rule these 2 out. There's this one sp3 carbon. It's an sp3 carbon bonded to an oxygen. Ought to come in 60, 70, somewhere like that. sp3 carbon bonded to an electronegative atom. So now we're down to 3 molecules. Well, on the last one, we figured out that there were 7 different carbons there, right? There's no plane of symmetry. So we got a carbonyl, and then all 6 of these benzenes are magnetically different, chemically different as well. Right? So it can't be that. How about the other 2? Okay, so again, I erased it for a reason. There's a plane of symmetry here, and it reflects. So 1. We got carbonyls. That 170.9 is probably going to be the carbonyl. The ranges I gave you, they're not like cliffs, right? So I said 110 to 160 and 160 and up. 161 could be an aromatic. It's really right on the border. We've got 2, 3, 4, 5. So because of the symmetry of the benzene ring, there's only 4 different, magnetically different carbons in the ring. Same thing is true on this one. 2, 3, 4, 5. And so just like the last IR problem I gave you, C13 NMR alone is not enough to distinguish these two. So if you worked it out, if you said, oh, it's that one, okay, good, you're close. You understand the NMR. But scientifically, there's no reason to say it's this one and not that one, or this one and not that one. So if you answered either one of these alone, good job, you're picking up the NMR, but don't go farther than the data. The data is always, in science, the data is everything, okay? If the data tells you it could be one of 6 things, you can't just guess which one it is, all right? And this is, it's 33 minutes in. I don't know if you're listening or not. This is one of the things that makes science policy so hard, is very often we don't have enough data to really make a decision, right? In the lab, what you do is you go get more data, right? But in real life, sometimes you got to make a decision. There's 3 options, and you got to sort of use your gut to figure out which one. This is a science class, so don't use your gut. These 2 are both options for this spectrum. If in real life, if this was in the lab, I would go and collect more data. I would collect an IR spectrum. Nope, an IR spectrum is not going to help me. OHs, carbonyls, in both. I would collect a proton NMR spectrum or a mass spec. These are going to weigh different. They'll have different molecular weights. So mass spec would give me a difference. And the protons, when we get there, right, we've got 4 CH protons here. We've only got 3 CH protons here. We'll be able to see a difference there. Okay, so when you guys come to never mind, I'll put it in an email. This is long enough.